afternoon, everyone. Do we have any questions before we get started? I want to make sure that everyone has a partner for the project. And so there are two ways we can try and find partners for people. You're working in groups of two. And so if you're still looking for a partner at the end of class, you can come forward, come on down front, and if there are a few of you, you can hopefully find a partner for your homework assignment. And if that, by chance, doesn't work out, then why don't you post a message in the under the forum for this particular homework assignment. Say you can do one of these, make a topic of looking for a homework partner, and then hopefully you can find someone. Because in some of the lab sections, there's an odd number of people, and so one person's left out. And I'd like everybody to have pairs, to work in pairs on the upcoming homework assignment. All right, so what I'd like to do today is three things. The first is that I'm going to actually show you a plot that I got from Swivel and have us sort of essentially kind of go through the kinds of things that I would expect you to do for your homework assignment. It's all application specific, so this will have to do with the particular data that I've pulled off of Swivel. Then we'll bring back that plot I showed you at the very end of class on Wednesday and do a critique using a set of general rules that Howard Weiner, a statistician, created called Weiner's Dirty Dozen of all things not to do when you're making a graph. And then if we have time, I'd like to end with a little story about a particular graph that was made in the 1860s and is considered one of the best graphs ever produced. So let's get started. So here it is. Here's this swivel bar plot, and what I'd like to do just right off the bat is take 2 minutes to have you talk with a partner and come up with some questions and critiques of this plot. Can you all see it pretty well in the back? So why don't you do that? Come take a look at it for 2 minutes and come up with some things that you think should be changed or should be further elucidated about this particular graph, which came from Swivel.
Yeah, there's no left, so I don't know which is more effective. And like the time scale is I guess right, so that
Are you asking me? Oh, no. All right. Let's get your first impressions. I'd like you to say just one thing, because there are at least 6 things you can say about this plot. Yes, you are. Andrew. Good. That's one thing. That's very good. We see there's a light green and a dark green, and we know that this is information about Democrats and Republicans, and we don't know which color corresponds to which party. All the way in the back, you are? You are? Manisha?
And I was wondering, with like the activity label the counties, and also I'm not sure if they're tracking one county over many years, right? Like 10 years. I'm not sure if the x-axis should be county names or years.
The y-axis, you mean, or the x-axis? Oh, you're saying there's a missing label on the x-axis, so you're not even sure what the underlying data are. Is this one county being tracked over many years, or is it multiple counties? Okay, someone else? Yes, and you are? Adrian? Right, so remember, those are our tick marks and our tick mark labels, and you're right, they don't line up below the plots. They're really poorly made. Do you have a guess of what those bars, where they, roughly what the actual years are for when the bars are? You are? Jackson? You think it's 4 years. So when the presidential elections, every 4 years, that's a good guess. You should be able to tell from the plot, and you have to guess. Some more. Yes, you are?
I'm
Teresa?
The Y label is really confusing because it just says majority of Democrats and majority of Republicans. We don't know if they're measuring like percentage-wise.
Right, it says the y-axis label says majority of Democrats and majority of Republicans, and majority meaning what? And we don't know, right? It says, the title says California Majority Party by County. Even that's a little bit confusing. One of the things that you'll be doing when you make your graph will be having a very detailed caption. And your caption should contain a lot of information about what you are plotting. So the caption's a very important part of your plot. How about a couple more? Yes? Name first? Pierce? Right, so you're coming up with a suggestion for how to improve the plot already, since we know it's Republican and Democrat. Why not use the standard political party colors of red and blue? Any others? Have we exhausted the possibilities for now? So there's real confusion about what the actual data are, and you might find that with the plots that you're looking at as well. And the good thing is that you can look at the actual data. So let's take a look at the next page. Here's the actual data that was used to make this plot. So take a look at it. And below that is the reference. It's one good thing on Swivel is that many people write down the reference as to where they actually got the data. And you see majority of Democrats, majority of Republicans, election year. Those are essentially those are the variable names. The first row is 21-37, 2004. Then comes 23-35, 2008. 29-29, 2000. 37-21, 1996. Is anybody saying, oh, no? And you are? Allie says it's out of order. It's out of order. And so, can you tell what was actually plotted? Can those of you who are up front, can you read the little numbers on the top of the bars? So on the top of the bars, not the bottom. Can you see that? How about you? Are your eyes a little better? Can you see what's written at the top? Let me go back one where it's a little bigger. There. Can you see it now? How about the far right 2 bars? 43 and 15. Okay, so let's go back and look at our data. Oops, things are going wild here. 43 and 15 are the data for which year? 1992. So this is totally screwed up. You've got years going along the x-axis, and they don't match the years from the data. It's being plotted in the order of which the first row is the first set of bars, and the last row is the last set of bars, even though the last row has to do with 1992. Okay, so how might we improve this? We've already heard a couple suggestions. One is, well, first here's a set of things that I came up with, and you'll notice that they pretty much match everything that you have mentioned. The x-axis tick marks are poorly located. They should be located at the actual years, the election years. As someone mentioned, it looks like it's every 4 years. The y-axis label is very misleading. It's actually the number of counties. We found that out, or I found that out, by going to the original source and saying it's actually the number of counties where the majority of voters were registered as Republican or Democrat. It would be good, as someone suggested, to use color, to use recognizable colors for the two parties, and the data are turned around. So one important thing when you're looking at any plot is to sort of say, what's the message that's coming through to me from this plot? So essentially, the question is, how has party registration changed over the past 5 presidential elections? I think that's what the creator of this plot's trying to get across. But before we go into my lurking variables issue, or my the other 2 comments, I want to say this is what you could do in R to improve that particular plot. So we have the years now. We have an x-axis label called election year. We've got labels below the pairs of bars that clearly mark the particular election year. Blue is for Democrat, red is for Republican, and there's a legend to just make sure that that is in fact the case. The y-axis is now labeled number of counties, and there's still, the title is California Counties Majority Party of Registered Voters. Okay? It's a slightly confusing concept. Why is this a slightly confusing concept? Eugene?
I don't think that's California.
It is California. It
There's
is.
a lot more Democrats still in the state than there are Republicans.
Oh, you have pointed out a very, very good thing. You said that you think that there are a lot more registered Democrats in the state of California than Republicans. I think that's what you said. Why does it not look that way here? Yes, you are? Tyler, why doesn't it look that way?
Number of counties, so perhaps like Democrat counties are a lot bigger and therefore have more Democrat voters.
This is not counting voters, which is something that makes sense that you would want to count. This is counting counties. And so if a county has a majority of Republicans in it, then it's going to be a red county. And you said that maybe some counties where the Republicans have the majority are actually have less population. What makes you think that that could be true? So this is, again, one of the things you could do with making your plot is you can go back and find out additional information that will help you interpret what's going on here. Can someone, all right, let's find out who in the class, many of you are from California. Many of you I know are from the Bay Area. Is there anyone, what counties are people from? Is anybody from a slightly, yes?
Kern County,
Kern County, where is that?
Bakersfield,
Bakersfield.
Central Valley.
Okay. Other counties? Yes?
San Joaquin County.
San Joaquin, and where's that?
It's like an hour and a half east of here, Central Valley.
An hour and a half east of here in the Central Valley, yes? Which? Ventura County, and where's that? An hour northwest of LA on the coast, yes?
Nevada County.
Nevada County?
3 hours northeast from here.
3 hours northeast from here. So you guys are from really different parts of the state, and can you make a statement about a possible connection between county population and the proportion of registered Democrats or Republicans? You want to try?
My
Warren?
county is like 97% retired Vietnam War veterans.
Your county is about 97% retired Vietnam War veterans, and?
All about being Republican.
And they're mostly Republican. You come from a very rural area. Rural areas tend to have larger counties in terms of geographically large counties, but a lower population density. We know about density with our density plots. It's the same kind of idea. And so this could be really very misleading because what you're looking at is a count of counties, that's not necessarily representative of the population. So that's great. So one way, so this is the next stage, is to say, well, what additional information could I get, or how might I improve this plot? By the way, the code for everything that I'm doing now have already posted on the web last night. And having technical difficulties with my display here. So I went back to the same website and found data that I thought was far more relevant to what I perceive the question to be that the creator of the graph was trying to answer. And that is the election year, the actual number of eligible voters, the number of registered voters, and then the proportion that are registered Democrat, Republican, some other party, or declined to state. What is declined to state? That's kind of special in California, and in other places it has a different title. Do you know what that is? Independent, so not affiliated with a party. What do you see here, just looking at the table of numbers? That gives a very different message from the bar chart or the bar plot. Yes? There's a huge increase in decline to state as we go from 1992 to 2008. And by ignoring those voters, you really skew the picture. So there's two things going on here. One is you're looking at counties, and the other is you're ignoring two other types of registration, which could impact the overall impression of the party allegiance of the voters in California. So let's take a look at a next plot. So this is a plot that I made instead. Notice it's not a bar plot. Remember, these are percentages at different years. There's no need to represent these as bars. If I had represented them as bars, I would put 4 bars next to each other for each of these election years, and I think it would be harder to see what's really going on. You can see much better in this plot where I've connected the points from one election year to the next. Each curve is a different color, and the color corresponds to the party. So the blue curve is Democrat, the red Republican, green the other. So all of the other parties have been lumped together, and black is declined to state. So take a look at this and tell me what impression you now have of the registration in the state of California in comparison to previously. Yes?
Before it looked like the Democrats were losing ground and there were a lot more Republicans, but now it looks like there are less of both and the decline to state voters are really.
Very good. Before it looked like the Democrats were losing ground as time went on and the Republicans were gaining. And now we see that it looks like they're both losing ground. They're almost parallel, decreasing slightly. And the one that's really increasing a lot is the decline to state. So that's a very different impression of what's going on in the state of California than that bar chart. And hopefully you'll think this one's far more representative of what is going on in the state in terms of voter registration and party affiliation. Okay, again, that's just to show you there's the code. We're not going to go through it, but I've put all this code up on the website, and I put these data sets up on my website so that you can, in fact, run this code and and recreate these plots if you like to. And so let's review the general terminology that we introduced on Wednesday. The scale, or in terms of the scale, we've got our horizontal scale and our vertical scale. We want to make sure that we label these and put tick marks and tick mark labels. And sometimes those labels are just fine, that R produces for us automatically, and at other times they're not. And then when they're not, then you have the ability to produce and locate them yourself. And some of the code that I've put on the website shows you exactly how to do that. The data itself, the plotting symbol that I used here were lines. We had a key, and which is also called a legend, which told you what color corresponded to which party. In particular, I didn't have any marker or reference line, but that's a line or a point or label that helps you sort of locate important events that might affect your interpretation of the data. Titles, subtitles, and captions. And there's also the issue of juxtapose versus superpose and inlay. So if we go back here and take a look at the actual picture, what I've done is I have superposed 4 line plots on top of each other. If I had juxtaposed them, I would have produced 4 separate plots. An inlay is when you have a plot inside a plot. So in a way, the legend is an inlay in my graph here. But when we refer to inlays, we really mean when you've got another miniature plot that's inside of a larger plot. What are we looking for when we're making our plots? Those two basic concepts. One's called clear vision, and the other is clear understanding. Clear vision says make your data stand out. Your data's got the message in it. Don't obscure it by having lots of chart junk and extra clutter in your data region. Put your clear understanding says put your major conclusions, if you're writing a report or a paper, put them in graphical form and provide reference information for them. In other words, have a very informative caption that can help summarize the data that you've plotted, including any type of reference information, the units, etc., and quickly summarize what you see, what you've found in your data. The idea of what kind of scale to choose, you want to choose a scale such that you include all of the data or nearly all of the data. If there's one really large outlier, that would, if you included it, then all the rest of your data would be hard to see. You don't include it and say in your caption that you have left out this particular observation. You want to make sure that your data fills the entire data region, and 0, 0 does not have to be on the scale. Your 0 doesn't have to be on either the X scale or the horizontal scale or the vertical scale if it doesn't make sense to put it there. And choose a scale for your data that improves the resolution to make it easier to see the basic underlying structure in your data. One thing I really want to get across is that making plots is a very iterative process. You don't do it, the code that I showed you, you don't get that code the first time you do it. I probably made a dozen plots before producing that final one. Some of it is you first want to see the structure, and then you want to make sure you put the more information you can add to the plot, the better, without getting it very cluttered. The other thing is it's also okay, not for this assignment, but in general, it's also okay to make more than one plot of the exact same data or the exact same variable if you're getting at a different aspect of what you found in the data. Okay, so let's now turn to Howard Wehner's Dirty Dozen. If you're interested in reading the full article, I've posted it on BSpace. Now I've simply taken examples that are from his paper in the 1980s, which is basically how to make really lousy graphs. Follow his 12 techniques. So we'll go through them one at a time, looking at his plots and sort of seeing what he means by his 12 rules. The first one is show as few data as possible. Can you see the data here? They're right there. There's 4 observations, really close to 0, 0. So that's not a lot, and it's not taking up much of the data region. That's rule number 1. Rule number 2 is hide the data you do show. Take a look at this. We're looking at public and private elementary schools over the period from 1929 to 1969. We see that the y-axis scale is in thousands of schools. And again, you might want to say, well, what's the message here? There could be, the way I see it, there could be 2 messages. One might be the number of schools is declining. If that's the case, then why bother showing us private versus public? Well, can you see much about public? Maybe another message is the number of private schools is increasing. These are called stacked bar charts. Stacked bar charts are really pretty lousy to look at when you want to make a comparison of the black parts of the bar from one to the next, because they're so small that it's really hard to tell the difference between the size of the bar above 1929 and the size of the bar above 1969. You can tell it's bigger, but it's really hard to tell how much bigger it is. And that's because the scale is such that you need to include all of the public schools, and that's the vast majority of all the schools. And so the private's been squished down to a very small part of that bar. And if your real message is to see what's going on with the private schools, this is not the way to see it. Alternatively, you could simply plot the private schools with dots, and you could connect the dots. So you can actually see the values over each of these decades. And you can even include an inlay of a table that it gives you the actual values. Now you see what? What characteristic do you see in terms of enrollments or numbers of total number of schools, elementary schools, private elementary schools, from the 1930s to the 1970s? What do you see that you could not see in the stacked bar chart? You can clearly see that they're increasing, and I want one other observation. Yes? There's a huge jump from the 50s to the 60s. There was no way you could see that in the previous plot because it was all squished down in those tiny little bars. Oops. So, let's go back. Hey. Let's see where we got to. Okay, here we are. Number 3, ignore the visual metaphor. These are 2 different examples of ignoring the visual metaphor. Let's take a look at the plot on the right. The plot on the right is split into 2 plots. So the canvas, I should say, is split into 2 plots. So these are juxtaposed. They're side by side. And then within each one, there are actually 2 plots, 2 graphs that are superposed. On the, it says the title for the whole canvas says U.S. trade with China and Taiwan. The one on the left is about China, U.S. exports and imports. And the one on the right are imports and exports for Taiwan. Can you see something fishy about that? Those plots? What do you see? The scales are different, that's right. And so if we want to easily go from comparing what's in one plot to the next, we should have our Y scale, our vertical scales, and our horizontal scales to be similar. What else? Yes?
Like the clear line for the right is U.S. imports from Taiwan, but then on the left one is U.S. exports to China. So it's like the lines aren't.
Right. If you don't read the text carefully in the actual plot, you would think that you should be comparing the black part of the curve, the 2 black parts to each other. But in fact, on the left side, it's imports, and on the right side, it's exports. So they've just colored it in order to have the bottom one, whichever one it is, be black and the top one be clear. Not a good idea. There's no need to even have the color. If that color weren't there, you would read the plot much more carefully. So that's the idea of ignoring the visual metaphor, is that you're ignoring the fact that anyone who's going to just quickly take a look at it, their impression is going to be to compare black to black, white to white. And that's completely the wrong comparison to be making, because one's imports and the other's exports. The other plot on the left are these huge three-dimensional bar charts. And so essentially what we mean here by ignoring the visual metaphor is that the information is one-dimensional. And you've created three-dimensional bars to represent one dimension. And that's not a good idea. You can get very misleading results, very misleading impressions, visual impressions, by doing that. Number 4 is similar to number 3. It says only order matters. What's going on here in the original chart, which is on the left-hand side, is that we're looking at the purchasing power of the dollar through the different administrations. The top is Eisenhower and the bottom is Carter. And what's been done here is that the width of the dollar bill, the long part of the dollar bill, starts with Eisenhower, and everyone else is done relative to Eisenhower. However, to make it still look like a dollar bill, they've shrunk all of the dimensions, the height as well, so that it still has the right aspect ratio to look like a dollar bill. The problem is, when you look at this, you are comparing areas. You're not comparing lengths. So in fact, from the Eisenhower administration to the Carter administration, what was worth $1 in Eisenhower's time is now worth about 40 cents in Carter's time. Is that dollar bill 40%? Is Carter's dollar bill 40% of Eisenhower's dollar bill? No way. What does it look like to you? About 25%. And that's because they've maintained the shape so it still looks like a dollar bill. So here, only order matters, meaning only one dimension matters, and you've created a two-dimensional object that you're making comparisons with. So although it looks really nifty, where this was done before, it was really easy to Photoshop things, and so they've been able to put the president's picture in the middle instead of the George Washington, but in fact, it's a very misleading graph. The one on the right is one piece of information for each year. You can simply make those little points, or bars in this case, and connect them and see how $1 in Eisenhower's time is now worth about 40 or 45 cents in Carter's time. And look at the shape of the decline. You actually see more information here. You see the curve as well. Okay, graph the data out of context. Here's something that appeared in 1981 in the New York Times as a complaint to the president's graph. So the president's graph is nearly an inlay in the New York Times graph. What do you see about the president's graph? It's the exact same data. What's the difference between the two? Simply scale. With no scale on the y, the horizontal, the vertical or the horizontal. And so it looks like there's a huge difference between our bill and their bill. But you have no idea what the actual magnitude of that difference is. You can see this when you're making plots in R. You can actually resize that the graphing window, and a difference between two things can look really different. A difference between two curves, the gap between them can look really big or really small, depending on if you make it like long and narrow or tall and thin. So the New York Times plot lets you see that the actual difference is a couple $1,000, which you don't get to see in the president's plot. Change the scales mid-axis. So notice here that It looks like the Post. These are two newspapers, the Post and the New Yorkers. The Post and the, what's the other one? The News, I guess. It looks like they're converging. It looks like the Post is about to overtake the News, until you notice that on the vertical scale, those of you in the back probably can't read this, it goes 500,000, 600,000, 700,000, 800,000, 1.5 million. And that's right where the two lines are merging. So the scale has been changed mid-axis, and the only indication of that is by carefully reading the tick mark labels. So it's quite deceptive. Number 7, emphasize the trivial. What this plot is there are two plots juxtaposed, females on the bottom, males on the top. This is years across the horizontal axis, 1968 to 1980. The vertical axis is dollars, and it's the median income for men or women, males and females, according to years of education. Now, what do you think Weiner means by saying emphasize the trivial for this particular plot? What do you think he's indicating? Why do you think he's saying this particular plot is emphasizing the trivial? Yeah?
It just looks really busy to the eye.
It.
And so
Mhm.
I think maybe whatever the different pattern lines represent is unnecessary.
That's true. There's a lot of unnecessary clutter in this plot. Those are the grid marks aren't really needed. That's not quite what he's meaning here about emphasizing the trivial, though. What were you going to say?
Is it maybe his categories are specific, and you should lump them together? Like, you've got between 9 and 11 years, you've got 12 years, 13, 16, like the difference of 2 years.
So you're saying that there's a lot of, well, they probably have a lot of data, but you're saying that what you're looking at is the years of education, and you're saying that it's finely cut up, and that maybe you could lump it together.
8 years is what? That's like not even.
That might be true, but that's still not what Weiner means by emphasizing the trivial. Were you going to say something?
I was going to say maybe they should just compare median income between they're all
Between,
female and male, but they're all plot is just way too much to analyze.
I'll take part of your answer, which is why aren't they comparing the median incomes between males and females? Because most of us take for granted that the more education you get, the more the salary will increase. And what we'd probably really like to see is how do males and females compare. And it's really hard to do that when they're on two different plots. And so how would you put that on one plot? Well, you'd actually switch and say, I'm going to, on the horizontal scale, I'm going to put education. And I'm going to have just two lines, one for males and one for females. So here's something you did not see in the previous plot. You see that there's a gap that's roughly the same size between males and females at every level of education. You could not see that in the previous plot. So that's what he means by emphasize the trivial. The previous one emphasized that the more education you get, the higher the salary is on average. This plot says that there's a difference between males and females. You still see that the more education you get, the higher the median income is. But you also see the difference between males and females. Number 8, jiggle the baseline. The plot on the left is essentially like those stacked bar charts. This is the U.S. imports of red meats. The bottom is beef and veal. The next one's pork, and the next one's lamb, mutton, and goat. And they're being added on top of each other. So not unlike the private school, public school stacked bar charts, it's really hard for you to see how has lamb and goat meat changed over the years? Or how has the pork import changed over the years because it's going up and down with the bottom one of beef. So instead, simply plot them as separate lines. And you could see that pork has increased, and goat meat and lamb and mutton has stayed the same, if not decreased a little. And it's really hard to see that in the left plot. Number 9, Austria first says just order it alphabetically, or don't even think about how you might display your data using another variable that has some kind of meaning. What's going on here is this is the life expectancy at birth by sex. Males are the vertically striped, females are the diagonally slashed, and you've got the countries that are ordered alphabetically. Austria's first at the top, Canada, Finland, France, Germany. Instead of doing that, why don't you order the data by life expectancy and see where the countries fall? So the plot on the right is a correction of that, where you've got the life expectancy in the middle. Coming off the left side are the women, and off the right side are the data for the men, and you see where the countries lay. This is really fascinating. You see that all the women have a life expectancy, no matter what country they're from, that's longer than for the men. And you also see the USSR at this time was way down there at 63. And so you can start making comparisons between countries. You can make comparisons between men and women. You can't in the plot on the left. Number 10, label illegibly, incompletely, incorrectly, and ambiguously. So again, we've got these three-dimensional bar charts, which are totally unnecessary. We also have these logos from the different airlines. But what you probably can't see from where you are is that, in fact, the data, it looks like there's commission of the payments to the travel agencies has dropped precipitously from 1977 to 1978. That's the third to the second. However, if you get your little magnifying glass out and you look at the words written in that little bar right above Delta Airlines, it says first half of 78. So what they've done here is they've got the entire year for 76, the entire year for 77, and only the first half of 78. So that's been labeled such that it's really hard to see what's going on. And if anything, what you'd want to do is project for 1978 and then make your comparisons. So the plot on the right is doing that. And you see, if anything, the commission payments to the travel agencies are on the increase from 77 to 78. Number 11, more is murkier. More decimal places, more dimensions. This is an example of a table where we now have 5 digits after the decimal point. And the question becomes, how many digits should there be? You don't need all of those. This is where R falls down because it doesn't know what you want. So when you ask for a mean, it's going to give you a mean to however many decimal places. And you have to decide what makes sense for your data. For height of women, if it's measured to the nearest inch, you probably don't want to report a mean to 6 decimal places. And last is, if it's been done well in the past, think of another way to do it. So in other words, if someone's done a good job, go ahead and copy them. Use what they've figured out. Don't say, oh, I can do it better, and in fact wind up with something worse. So given the time, what I'm going to do is I'm going to go through one more example of the, so I'm not going to be able to get to, on Monday, we'll get to the really famous plot. But for right now, what we're going to do is, again, look at the plot I showed you at the end of class on Wednesday, and really quickly sort of talk about how we can fix it up. So here's the data. This is data on the Intel chips from when they were first introduced in 1974 to 2004. So every chip has transistors on it, and you see the increase in the number of transistors. The chips are a certain size, measured in microns, and you see the decrease as to how they get smaller and smaller, or thinner and thinner. the clock speed tells you how fast a computation can be done. And you see how these chips are getting faster and faster in terms of clock speed. The data are, this 8, 16, 32-bit. And MIPS stands for millions of instructions per second. And you see how, again, that's increasing. So here's my plot. That I showed you on Wednesday. So I've got 4 minutes left, and I want you to take 1 minute to talk amongst each other to say, I've worked really hard to get this. R doesn't produce such a plot that easily. I want you to make criticisms using the 12 things that you've just heard about and a clear vision and clear understanding to say what I've done wrong with making this plot. 1 minute. Talk amongst yourselves, and then I'll ask you.
I don't know if there's data there or if there isn't. I think that's so if you using like blogs or something so that we can see that stuff over there if there's stuff.
All right, your time's up. Hopefully you've got lots of things. You should come up with we should have at least 6 things wrong with this plot. So 1 thing from each. Yes? No title. That's correct. There's no title. Yes? The colors are ugly. Even if they were my favorite colors, not only they might be ugly, but even if they were my favorite colors, what's the meaning associated with those colors? None. They're completely unnecessary. Another. You must have gotten past that. Yes? No, what kind of labels? No labels on, well, actually, in fact, there are labels, but they're not very helpful labels. There's a label on the horizontal axis, which is just the variable that I've plotted. And that's chips dollar date. And on the vertical axis, it's chips dollar transistors. So more informative labels would be much more helpful. Yes?
The years 75 to about 90 seem like they're about the same.
Yeah, you can't. So this is where you want to basically have the data fill the region. And in fact, what's going on is the data for 2004 is entirely dominating the plot. It looks like there's no change from 1974 to 1990. Yes? Oh. How about you? Very good. Why not use a log scale to see about the growth? If something in computing, things typically double every year or so. And so if something's doubling, it's going to shoot off like an exponential curve. And so if you want to see if it is an exponential curve, you take logs, and you should see a line, right? So let's quickly look to see. I did some of this. Let's go to the next one. These are what I found wrong. There it is, redone, still not. I got rid of the colors. Nobody mentioned the grids. The grid was all this extra junk that wasn't necessary. It's on log scale now, and still the labels and stuff are missing. Now let me say one more thing, is we had a lot of data about the change in transistor, or change in chips over time. And I'm just going to put this one up as a parting picture. This is more things we could do. And here it is. This is my parting picture for you. I've now put transistors, clock speed, MIPS, and microns all on the same plot by making them all relative to when the chip was first made. So they all start at 1. The scale is still log scale. And I've put my own tick marks and tick mark labels. So you see 10, 100, 1,000. I've got labels on my horizontal and vertical scales. And you can see that things have been moving exponentially. And in particular, transistors and MIPS have been going together. And microns, the things haven't been getting as small quite as quickly as the rest. This is now data rich, fills the screen, has lots of labels and information. Have a good weekend, and on Monday we'll talk about one of the greatest graphs ever.